So the goals for today's lessons are to identify the types of bonds that we have, ionic, polar covalent, nonpolar covalent, and to represent these types of bonds using appropriate symbols, which I will teach you. I would like for you to first try and do 1, 2, 3, and 4 on your own. Take a few minutes, try these on your own, and then come back to the video when you're ready for a check. Number 1, you could draw any covalent bond. This would be between a nonmetal and a nonmetal. For instance, you could draw CH4, where you have carbon bound to 4 hydrogens. The important thing here is that you're drawing the Lewis dot structure. For number 2, again, you could draw any various type of ionically bonded lattice. Just make sure that you are drawing a lattice and that you have many of them and that you're using the bubble structure for your picture. So let's say, for instance, I wanted to do sodium oxide. So I've got sodium, my oxygen, and another sodium. Then I'll put another oxygen on here. I'll put another oxygen on here. Sodium here. I have another sodium here. Oxygen. Sodium. And another O2 minus. And so on and so forth. And there is our lattice. For number 3, the pictures shown below represent different types of bonding. So match each picture with the one of the following. So H2, you might guess that this would probably make something that looks the same, as in they're the same element, so the structure should look very symmetrical. And so that would probably go with this one. HCl, we have them covalently bonded, but they might not look very symmetrical based on their individual properties, which we haven't quite learned yet. But you might be able to guess that that one is this one, because at least it's still a covalent bond. And the last one, we have salt, NaCl, would go here because we have ions, this one being the sodium and this one being the chlorine. And those would come together to form an ionic bond because they're attracted to each other because they're oppositely charged. Provide a possible explanation for what the gray blobs represent in the picture above. So you might have guessed that these represent electron density or some sort of electron cloud or the electrons surrounding the nucleus, and that would be correct. So that is what they are representing. Okay. Use the models shown below to explain how an atom can end up with a charge of minus 0.20 through the unequal sharing of electrons in a covalent bond. So we're going to look at this in 2 different ways. Let's start with one where we are equally sharing our electrons. Like this picture, we can imagine that the electrons are kind of evenly shared in the middle of these 2 nuclei. So I'm going to draw a little dashed line down here that represents the middle of our 2 nuclei. And that means that 50% of my electrons are on this side, and 50% are kind of being pulled to this side. 50% of 2 electrons is equal to 1 electron, which would be a minus 1. And same on the other side, 50% of 2 electrons is equal to minus 1 charge. So they're each sharing equally, so technically it's like they're both feeling a minus 1 charge. Each of these nuclei have a charge of plus 1. So the overall felt charge of each of these would be 0, which you might be able to assume if they're sharing them equally, if there's no unequal sharing of the electrons, then both of them should have the same charge, which should be 0. Now, how do we get to this unequal sharing with this minus 0.2 charge? So we have our 2 electrons evenly in the middle here, but what if we were just to move it slightly towards one side, maybe there? Still kind of have our halfway point. So let's say, for instance, that on the left side over here, now it has about 60% of the electrons. So before it was 50-50. Now let's say it has 60% of this electron density towards it. So we do what we did before, except now we're using different percentages. So 60% of -2 is equal to negative 1.2 charge. And on the other side, conversely, if 60% of it is on the left side, that means 40% of our electron density is on the right side. So times our 2 electrons, times our -2. That'll get us a charge of -0.8. And so if we add these to our nucleus charge of +1, we get a charge here of -0.2, and here we get of +0.2. And you can see here, by this unequal sharing of the electrons, we can end up with this kind of partial charge. It's not a full charge because it doesn't fully have the electrons around it. It's kind of unequally pulling them towards it, kind of like a tug of war. And in that, it just kind of has more of the electrons on its side, making it slightly negative. This is where we use these signs called delta. This sign is a little bit negative, so that gets a delta minus sign because it's slightly or partially negative. And on the right side, it's partially positive. So that's what these mean. Partial negative and a partial positive. They're partially charged. They're not fully charged like they would be here. These are fully charged. These, where more of the electrons are kind of sitting over this way, has a slightly negative charge. So next, we're going to look at what's called electronegativity. Electronegativity is a value that has been assigned to atoms, and it's kind of thought of like their tug-of-war strength. It can be used to predict whether electrons are shared equally or unequally. And this is located on your periodic table. So here we have the electronegativity chart, and we are looking for the electronegativity of hydrogen, carbon, nitrogen, oxygen, fluorine, and chlorine. And those are the numbers that are written in the box here. So hydrogen is 2.1, carbon 2.5, nitrogen 3.0, oxygen 3.5, fluorine 4.0, it's the most electronegative, and chlorine 3.0. These numbers determine how strong they are. The higher the number, the stronger it is. So fluorine is our strongest element. It's going to pull electrons towards it very strongly. So we can fill this in back here. Hydrogen was 2.1. Nitrogen is 3.0. 4.0. Carbon is 2.5. Oxygen is 3.5, and chlorine is 3.0. These numbers have no units. They're relative numbers. So they looked at the unequal sharing of electrons between two atoms, and they assigned it an arbitrary number. So they're all relative to each other. So the atom with the higher electronegativity has the stronger pull. Based on this definition, which atoms listed in question 7 would be equally matched in a tug of war? So ones that are the same. So the ones that are the same for us are nitrogen and chlorine. They both have 3, which means the electrons are going to be shared evenly. If atoms are evenly matched, then a nonpolar covalent bond is formed. Some examples of this would be like chlorine gas, hydrogen gas, bromine, NCl3, oxygen gas. You can also have ones that are very close in electronegativity, and so there won't be a tug of war. For example, carbon and hydrogen are close enough in which they will equally share their electrons, so there won't be a tug of war. So CH4 would be nonpolar. If one atom has significantly higher electronegativity than its bonding partner, a stronger pull, that means that a polar covalent bond arises, as in there's a pull. Like the Earth, there's the North Pole and the South Pole, and they're opposite. A pole in chemistry is a negative side and a positive side, so that's why it's called polar. The winner of the tug-of-war gets the partial negative, represented by the delta minus, and the loser gets the partial positive, represented by the delta plus. Some examples of this would be like water. As we can see here from our numbers, oxygen is much more electronegative than hydrogen, so the electrons are going to be pulled towards the oxygen, giving it a partial minus, and our hydrogen's a partial plus. Another example of this would be HBr. Again, bromine, much more electronegative. It will pull the electron towards itself. HCl. Again, chlorine, much more electronegative than hydrogen. In this class, bonds will be considered nonpolar if the difference in electronegativity between the bonding atoms is less than 0.5. So for example, if we looked at carbon and hydrogen. So carbon has an electronegativity of 2.5 and hydrogen has an electronegativity of 2.1. The difference between them is 0.4, meaning it's going to be nonpolar. This means that electronegativity differences of 0.5 and greater require you to draw the delta plus and the delta minus. Another example would be like nitrogen and fluorine making a bond. Nitrogen has an electronegativity of 3.0 and fluorine has an electronegativity of 4.0. So if we put those together, that means our fluorine has a delta minus because it's partially negative. It's going to pull the electron towards it. And nitrogen will get our partially plus because it's not going to have as much electron density around it. A molecule with many bonds requires that you analyze each bond separately. So let's look at methanol. So first I'm going to draw the bonds. So I've got a carbon bound to an oxygen, which is bound to a hydrogen, which is bound to a hydrogen, which is also bound to two more hydrogens. So we have to look at each of them separately. We look at every bond by itself. So first I'm going to look at this bond here. Carbon and hydrogen have similar electronegativities. So that means that this bond with hydrogen is going to be nonpolar. This hydrogen is nonpolar because they're equally sharing their electrons. That would be true for all the other carbon-hydrogen bonds, nonpolar, which is represented by this lowercase np. Then we look at carbon and oxygen alone. We're just looking at this bond now. When we look at the electronegativity differences between carbon and oxygen, it is greater than 0.5. It's a difference of 1. So that means that the electrons are going to go towards the stronger one, which is oxygen, because that's 3.5 and carbon is 2.5. So the electrons are going to go this way, giving this a partial negative and our carbon a partial positive. And lastly, we look at this bond between oxygen and hydrogen. Again, we've got 3.5 and 2.1. That is larger than a 0.5 difference, and the electrons are going to go towards the bigger number, so they're going to go this way, giving our hydrogen a delta plus charge. And that is how we look at that.